Circular motion. So I'm talking about the more broad subjects of circular motion. So the first one is just uniform circular motion and defining it. So basically, if an object is moving in a circle and velocity is constant throughout that circle, then it is in what is called uniform circular motion. And the speed is constant, but since the direction is rapidly changing, then you have an acceleration that's positive. And the acceleration, or the centripetal acceleration, is always directed towards the center of the circle. And the equation to find what the acceleration is v squared over r. And also the net force is also directed towards the center of the circle. And the same equation where F net equals ma that we use for everything applies to this too. So the next big concept is universal gravitation. And the situation used to describe universal gravitation is where you have two objects of mass 1 and mass 2, and they are r distance apart. And in order to find the force exerted between them through gravity, you use the equation where it's g, the gravitational constant, times m1 times m2 over r squared is the force of gravitation between them. And the gravitational constant, which is resembled by the capital letter G, is 6.67 times 10 to the negative 11th, so tiny number. And an important thing to remember with this concept is that when you have the equation G m1 m2 over r squared, the force of m1 and m2 on each other is equal. So the force of m1, the gravitational force of m1 on m2 is equal to the gravitational force of m2 on m1.
For my part, I'll be describing some key points in circular motion, and I'll be discussing planetary gravity, apparent weight, and weightlessness. When an object is in circular motion, the time it takes to complete one revolution is called a period. The period is expressed as an uppercase T. Period is used in many equations for circular motion, including for frequency and for velocity. Frequency is how many times an object completes a revolution per second. It is modeled as f, and f is the inverse of the period, so t to the negative 1. To relate the period and frequency to velocity, you use two equations, 2 pi r over t and 2 pi r f. Moving on. Apparent weight, also called centrifugal force, is a force you feel but would never show up on free body diagrams. When you are in circular motion, like a car going on a turn or a roller coaster on a loop-de-loop, apparent weight is the contact force that is supporting you. When a passenger is at the bottom of a roller coaster, the net force is pointing upwards at the center, and therefore the normal force is greater than their actual weight. This will cause them to feel heavier. So if you're going down and you hit the bottom, you will always feel heavier than you are at the top. When they're at the top of the coaster, upside down, the normal force and the weight will add together, making a net force downwards, which will cause you to feel a little weightlessness and a little lighter. Apparent weight can also help us find the critical speed of an object, which is the slowest speed at which something can complete the circle. It is represented by the equation Vc equals root gr. The critical speed is most related to orbit, because when an object is in orbit, it is traveling at its critical speed just about to fall into the planet. Next, gravitational acceleration of a planet is how hard the planet is pulling down on an object. This number can be calculated using the equation gravity of a planet equals the universal gravitational constant times the mass of the planet over the radius of the planet squared. G in this equation is the universal gravitational constant, which is 6.67 times 10 to the negative 11. The outcome of this gravitational force will vary from planet to planet depending on the size of its mass. Here on Earth, it is negative 9.8 meters per second. There's also a way to find the force of attraction between two objects, big or small. You can use this equation. The force equals the gravitational constant times the mass of the planet times the mass of the second object over the radius. The radius in this would be the distance from one center to the other center. This equation written like this would be used for the force between a planet and a small mass, but you can also do it between any two masses. You would just tweak the equation to exclude the mass of the planet, exclude the mass of the other thing you want to use. And this would still work.
So, for my part, I am covering orbital motion and bank turns. That's orbital motion right there. So imagine the moon is orbiting the Earth. This is what is known as orbital motion, right here. To find the velocity of the moon orbiting the Earth, you would use the equation V equals the square root of capital G, capital M over R. Capital M represents the mass of the central object, which in this case is the Earth. R represents the distance between the orbiting object and the object being orbited, which again in this case is the Earth. Capital G is the gravitational constant, which is the tiny little number that's put in a few equations. But if you want to find the velocity of an object in low orbit, you would use the equation V equals the square root of G times R. To find the period of something in orbit, you would use the equation T equals 2 pi times the square root of R over G. The period and radius are related using the equation T squared equals 4 pi squared over capital G, capital M, all times R cubed. Alright, orbital motion gone. Bank turns. In the Indy 500, cars go around a big oval track. And on the curves of this track, it has something called a bank turn. The bank turn allows the car from slipping and like making the fast turns, right? So the forces that keep it on the track are centripetal force and friction force. Centripetal force is calculated using the equation M times V squared over R. Centripetal force should be equal to the friction force, because if they're not, it's slipping right off the track. The acceleration of an object on a bank turn is directed to the center and the bottom of the track. The velocity and the radius of a bank turn are related to the angle of the bank using mg tan theta equals mv squared over r. The normal force of an object on a bank turn is perpendicular to the bank.
All right, welcome to Samuel's laboratory. Safety first, of course, right? All right. So in this lab, we're going to be needing a leader or just a line of some sort, a tape measure, scissors, a cup, and water. So first step, we will make 4 holes in the cup, and then we will thread the line through. I'll update in a sec. So now I have cut the 1/2 meter, 1 meter, and 2 meter cords. Okay, so now that I've cut the holes and strung the line through, I've made almost a harness to tie on the 1/2 meter, 1 meter, and 2 meter lines that I'm about to cut. I will update you those shortly. Next, I will use a 1 meter line and I will attach it to the cup. I will fill up the cup with 25 grams of water first and spin it around me at a constant rate or constant velocity for 10 revolutions. And I will take the time that it takes and I will divide it by 10, and I will have the time it takes for 1 revolution. After doing that with the 25 gram, I will do that with the 50 gram and the 75 grams of water. And I will take all those times and collect it in my data table. Then I will use the time for 1 revolution and convert it to velocity. After I do that for each individual 25, 50 gram, and 75 gram, I will move on to the next step. And that will be using all the different lines with 50 grams of water in the cup. So I will start off using the 1/2 meter line, attach it to the cup, and spin it around me at constant velocity for 10 revolutions. And I will take the time of those 10 revolutions and divide it by 10. Then I will have time for 1 revolution. I'll do that for each size line. The half meter, the 1 meter, and the 2 meter line. Boom. Once I have all those times, I will convert it into velocity. And then I will notice a change with the amount of water, the weight of water in the cup and the time. And then I'll also notice that the length of the line and the time and the velocity, it'll just all make sense. Thank you for visiting with Samuel's lab. Always remember, safety first.